Well, folks, I do greatly apologize. Murphy's Law just had trouble connecting to the internet. So nonetheless, my name is Rod Ramondo. I'm with the U.S. Department of Energy. I'm the Director of the Technology Development Office. And I'll be presenting to you today 3 integrated research projects for which we are participating with the Office of Nuclear Energy. And first of all, I want to extend our thanks again to the folks in NE and the folks at Idaho National Lab who have made this such a seamless and easy process for EM to participate, and certainly are very grateful and certainly be with the opportunity to engage with you folks. So this is our 2nd year. We are primarily focused on robotics technologies as an enabling technology for the Office of Environmental Management, and in particular our mission because of the nature of the work that we have in the coming decades, where it really demands the use of remote technologies, robotic technologies to help us accomplish our mission. And in that regard, we are focusing on robotics. And my presentation is broken up really into 4 different sections. For those who are not familiar with the Office of Environmental Management, I'll spend a few moments just giving a very quick background on who we are and who we are not and the challenge that we have in front of us. And then I'll get into each of the 3 integrated research projects. So I'll first get into our mission, the overview of EM. We were established in 1989 to address the legacy left by the Manhattan Project, which was, of course, the U.S. government's effort to develop the atomic bomb, and then the ensuing Cold War nuclear arms race, where we were in competition with the former Soviet Union for really nuclear supremacy, and of course, part and parcel with that is defense supremacy. So over those 4 decades, we built quite an infrastructure for maintaining and having the nuclear arms stockpile that we have, and we continue actually to manage today in good stewardship. We're also responsible for addressing the legacy left by the early years of government-sponsored nuclear science and technology research. So up until the point where much of that work had been transferred to civilian control, the government had responsibility with that, and actually sole responsibility for executing those types of missions. So in terms of our wheelhouse and the scope of work that we are responsible for addressing, it is just that, the legacy that was left by those 3 major initiatives that the federal government had. So if I take a look at our work scope in general, we have really 6 primary areas: nuclear facility decommissioning, which is essentially dispositioning the massive infrastructure that we have across the DOE complex. Associated with that is soil and groundwater remediation. We've had actually a lot of success in the last 25 years, obviously, because that is where the high-risk areas were that we had to address in terms of mitigating the insults made to the environment and doing what we can to ensure protection of human health and the environment. And associated with that mission of cleanup is the disposition of the radioactive liquid waste that we have generated through nuclear fuels reprocessing. The efforts to recover the raw nuclear materials needed to support our weapons stockpile. We've generated over 100 million gallons of highly radioactive, highly chemically reactive, and very complex liquids that we now have to disposition. Our preferred disposal or disposition path is vitrification, where we turn that liquid into glass. We also come up with alternate methods where we basically solidify it into a grout-like cementitious type disposition or final waste form. We are responsible for also closing our underground storage tanks. We have quite a bit, over 100, spread between Savannah River site in Aiken and the Hanford site in Washington State. Nominally about 1 million gallons in capacity. So a part of this mission is to dewater them, de-inventory them, and eventually close them. We also have, associated with that, is the disposal of our solid radioactive waste, as well as the hazardous waste and industrial construction debris that we generate from our operations. We do operate several waste disposal treatment, storage, and disposal facilities. What's shown in the picture there is our waste isolation pilot plant in Carlsbad, New Mexico, within which we dispose of our transuranic radioactive waste. Those are essentially our long-lived isotopes. Long-lived meaning they have radioactive half-lives of anywhere from hundreds of thousands to millions of years of decay. And then we have a number of surface or near-surface land burial sites across our complex, primarily at Hanford site, Savannah River site, and Oak Ridge National Lab. As you can imagine, we have a spent nuclear fuel inventory and special nuclear materials inventory that we manage, we maintain, and in some cases we disposition. So that is part of our mission as well. And finally, science and technology. That was critically important in the early days because when that legacy of cleanup was given to the department, very little technology actually existed to be able to remediate the environment, especially the environment that was contaminated with both radionuclides as well as chemical contaminants. So if you think back to the 60s and 70s and 80s, very little technology was available at that time, so there was a huge investment by the department in developing those remedial solutions so that we can mitigate the risk and insult to the environment. Just to give you a sense of the footprint of the initial challenge that we have, when we were chartered in 1989, we had a footprint which basically spanned the entire continental U.S. We did have contaminated facilities at Alaska, Hawaii, and some of our territorial islands. We have successfully remediated them. Some of them are in long-term care. But for the most part, our footprint was pretty broad, pretty big. Where we stand today, since 1989, we've invested about $152 billion in the cleanup. A large majority of those sites have been remediated. What's shown on the map now is really those facilities that are left, or the states within which we have facilities to complete our mission. There's two sites in particular that are the elephants in the room. One of them is the Hanford site located in the southeastern part of Washington State, and then Savannah River site on the western side of South Carolina. I mentioned our waste isolation pilot plant in Carlsbad, New Mexico, which is in New Mexico, and we have associated with that cleanup also at Los Alamos National Lab. And And in terms of our to-go scope, there is anywhere from $250 to $350 billion left of work scope in front of us, and spanning over anywhere from a 50 to 60-year period. So in terms of mission, it is certainly one that has a number of years to complete, but it's also one where when you take a look at the facilities that we have to yet complete, that is where much of our high hazard, high consequence materials exist. And these are the facilities for which it is really prime for the application and utilization of robotic technologies. So EM is undertaking an initiative to capitalize on the investments, or excuse me, on the advancements, I should say, that were made in robotic technologies in the last 7-8 years, and seeing what we can do to leverage that investment, and to the extent that we are, help advance the technology, particularly as we start dealing with our high hazard, high consequence materials. Just to give you a sense of the budgets, nominally we're at about a $6 billion budget annually, and now keep in mind this is taxpayer dollars. So we are the federal government is mandated for cleanup. So in many respects, we are a federal financial liability to the U.S. government, and our taxpayers, Congress, and the President nominally fund us at about $6 billion. And what should stick out to you right away is the blue sections of that, of those two pie charts. which is our tank waste program. I mentioned the liquid waste challenge or mission that we have. Our focus now has shifted from soil and groundwater remediation, albeit we still have contaminated environmental media that we are addressing. But for a large part of it, we are focused on our tank waste mission now in dispositioning our high-level waste fraction. And then to a lesser degree, decontamination and decommissioning, which is shown in the red. Now, soon after the tank waste mission, we make progress on that. The profile of that pie chart will shift, where now much of the focus becomes on the decommissioning of our nuclear facilities and the associated infrastructure. So there's going to be a natural shift just because as we evolve through our mission, the D&D of our nuclear facilities will take center stage, much like tank waste is doing now. And what that means is, from a robotics standpoint, is that while we have immediate needs in tank waste, we are in the process of also preparing for the future and the eventuality of decommissioning our nuclear facilities. So again, in terms of the EM mission and the legacy that we have to address, the opportunity for robotic technologies and remote technologies is now, and certainly within decades to come. So I'll get into robotics and what we're interested in. Again, I did mention that robotics, from our standpoint, is a tool, but it's a very important enabling tool. And for us, rooted within the fundamental EM mission is this concept of the science of safety, where we are now taking a look at scientific and technological advancements that are made not just in robotics, but in instrumentation, in modeling, in software, and applying those to the routines of our work planning and execution, so that we are able to afford a work environment that is safer for our workers, and also from an operational standpoint is more efficient in the execution of that mission. And overall, while we are focused on safety, what we are striving to do is, again, reduce that liability that the federal government has in the legacy cleanup. And again, for robotics, we see that as a very, very important enabling technology for us. In terms of how we need or what we need robotic technologies for, again, I mentioned some of this already, handling of high hazard, high consequence materials and waste. And you may have heard this in the past, and certainly applies to EM. Those tasks that are dirty, dull, and dangerous, we've actually added a fourth, meaning difficult, where much of our construction type, deconstruction type, and industrial type activities are very difficult to perform for a number of reasons. And for us, they require a significant amount of engineered work to be able to, for us to be able to accomplish that. So in terms of robotic technologies, it certainly provides an opportunity to more smartly and safely do or execute these tasks that are difficult. There is a heavy focus on worker safety, both from, there's a heavy focus on workers, both from a safety standpoint and a work performance standpoint. So in terms of worker safety, and I'll get into this later with one of our IRPs, we are looking at exploiting those robotic technologies that will allow our workers, that will provide them added protection and safety as they execute their routine tasks and the normal course of work that they do. And also in taking a look at what they can do and what they can't do. Are there opportunities to enhance their capabilities, enhance their performance, so that we are more productive and we're more efficient with our daily operations? We also are looking at robotic technologies as one of those key assets in responding to operational upsets and emergencies and even disasters. So to the extent that we can get robotic technologies that are easily deployable, and that's much easier said than done, but certainly we want to exploit the advancement of the technologies and have that as part of our emergency response apparatus. And I already mentioned about worker safety or worker efficiency. The same thing is true for facility operations, where there are a number of opportunities for robotic technologies to help us be more efficient, fundamentally with facility operations. And that does include to a small degree automation. So let me jump now to IRP number 1, wearable robotic devices for workers. The concept is very simple. Oh, by the way, so I am the federal point of contact up here in headquarters, and our technical point of contact is Tom Nance out of Savannah River National Lab. This particular IRP we are targeting for 2 years at $1 million investment, and the overall objective is to develop a functional prototype of wearable, prosthetic, exoskeletal, bionic, and other attachable human-assisted robotic devices that can serve really 2 functions. One, to serve as smart, protective, personal protective equipment, and I'll get into that what specifically we're looking for. And 2, as a performance augmentation and application device. So first, on the worker protection standpoint, it is really intended to help prevent workers from sustaining internal injuries. And this is really focused on how the body moves, how it responds to different motions, and doing what or having these devices be outfitted and equipped to help prevent some of those things that I've listed here, like overexertion, fatigue, hyperextension, over-rotation, abrupt movements, so forth and so on, and even the effects of aging. Now, there's a lot of technologies that have been already developed, albeit they have been focused on medical, occupational therapy, certainly the health and medical industry. To some extent also they have been developed for military applications, and even to a smaller degree sports. So what we are looking to do is leverage off of those technologies, those approaches that have been already developed, and seeing what we can do to apply them to the broader workforce. And of course, while we are focused on the industrial type, heavy lifting, very labor-intensive activities, that doesn't mean that it also cannot be applied for administrative type functions as well. But as you can see on the map, or on the view graph there, we are looking at really injury prevention as a key component of this type of wearable device. Part of what we are looking to make these wearable devices be is smart, where there is some feedback mechanism to the worker to advise them, alert them, or signal to them that perhaps the motions they're about to undertake is not ergonomically correct or would cause added stress to the muscles or joints or even the bones. So we're looking at technologies and sensing devices that can help provide that type of information to either the worker immediately or to supervisors or certainly health professionals that can use this information to again improve the health and safety of our workers. So integrating these types of devices into wearables is a key feature that we would like to that we are pursuing. The other part is this concept of so what's the difference? I mentioned that the smart PPE for which we are pursuing in terms of robotic devices is focused on internal injuries, and this is different from traditional PPE, which are really designed to protect workers from external hazards. So as what's shown there are all kinds of things that our workers, all kinds of hazards and risks that our workers face on a daily basis, and we outfit them with personal protective equipment. In contrast, we are looking at wearable robotic devices that to some degree can also accomplish that, but to a larger degree help prevent internal injuries. The other aspect of this is performance amplification and augmentation devices. Basically, these types of technologies, wearable technologies, that can help ease the performance of tasks that are physically stressful or demanding on the body, even mentally taxing, certainly ergonomically challenging, and I mentioned some tasks that are even beyond human capability. So as we take a look at those things that are labor-intensive and tend to be demanding on the body, we're looking at how can robotic devices provide them added performance or increased performance, and in the end, increased productivity. So in some regards, we're looking at the devices that can actually do both, serve as smart PPE and as amplification and augmentation devices. In terms of this particular IRP, there are 4 requirements that we have, and it's really not to focus on the technology itself, but actually building the team that can help deliver on this. So we are requiring that a particular principal investigator from a university partner with one of our national laboratories and any other federally funded research and development research centers. So the idea here is to get the intelligence and the knowledge and the practicality from the industry and then certainly our national labs and incorporate that into the design and into the features of our wearable devices. On a similar regard, we would like these universities to partner with at least one other U.S. university or college, and for us, it's really an attempt to increase the capability of our university system, particularly when we start looking at nuclear applications of our robotic technologies. Certainly building that bench and building the capabilities within the U.S. Will serve the federal government well. And because, again, EM has a very long mission ahead of us, when we talk about building the bench, building that field of expertise and that pipeline of expertise, we certainly want to do our part in establishing that as a national initiative. So we are requesting that PIs partner with or collaborate with another university. In terms of the technology itself, and I skipped over this on number 1, and I apologize, I hinted to this. We are looking for technologies that you're not starting with a blank sheet of paper. There's been so many advancements already made in the medical, health, military, and even sports industry that we want to leverage those technologies and see what we can do to adapt, modify, and tailor those technologies where it can be a tool more broadly used within the workforce, within the broader industry. So we are looking at leveraging off of existing technologies and investments as we move forward with this particular IRP. And then the 4th requirement is whatever we deliver or whatever you deliver, we want a device that we can actually take to the field and take to one of our sites and actually have one of our workers wear it, demonstrate the utility of it. So we are looking for a functional prototype to be delivered at the end of this. So I did mention that it is a $1 million award, and much of that is really focused on the fact that we're not expecting to, again, start off with a blank sheet of paper and leverage off of existing technologies that are out there now. In some respects, there is this element of technology transfer, albeit a slightly different application. I'll move on to the next integrated research project, and this is robotic telemanipulators for glove box and hot cells. Much like the others, I am the federal point of contact. Tom Nance is the technical point of contact at Savannah River. This is also 2 years at $1.5 million. And for here, we're looking at, again, functional prototype of telemanipulation in glove box and hot cells. And basically what we're looking for is robotic arms and hands, those types of devices that can be integrated and teleoperated by our workers, integrated into glove boxes and teleoperated by our operators and lab techs. And the reason for it is we are looking for increased ability for performing work within the glove box. We're looking at improving the efficiency, capability, and again, safety. And all of that all stitched together in the next few slides. Instead of putting words, I thought I'd put up pictures. Glove boxes are basically containment enclosures within which we handle our radioactive materials. We do it, these structures are designed where the materials are completely enclosed within this containment structure, and workers are able to access it and handle it through glove ports and gloves. And what you can see right away is that from an ergonomic standpoint, it is very difficult to work. The lower right-hand corner, matter of fact, shows a lab tech on a stool just to get access to the glove ports and do the work. So what we're looking for, again, certainly from an ergonomic standpoint and a safety standpoint, outfitting these types of glove boxes with robotic-type arms and hands, which can be teleoperated. So the concept is that the device be integrated and installed onto a glove box, and it be remotely operated, teleoperated by an operator or a lab tech. The lower left-hand corner kind of gives you a sense of some of the complexities within our glove bags and glove boxes. So those are the types of environments and challenges that we have within the glove boxes themselves. Another, on the next slide, what I show is try to give the sense of type of some of the tasks that we have to perform. Some of them actually do require fine motor skills, and what you see there on the larger picture is a lab tech doing work that again requires fine motor skills, and much of that is lost just through the positioning of your arms relative to your torso and having to work through these very thick rubber gloves. And these other pictures just give you a sense of the types of challenges in visibility, access, maneuverability, dexterity that our lab techs and operators face. Again, more pictures there that show kind of the awkwardness in working with this, with these types of glove boxes. So we are looking at taking advantage of the availability of technologies that can replace these glove ports with integrated systems. The same thing true is for hot cells. Hot cells tend to be more robust. These are typically physically built into our facilities. Very thick walls, very thick lead shielded and sometimes borated glass, several feet thick. And the reason for this particular design is because we are dealing with some of our highly radioactive materials, and we need the added shielding to be able to handle them. And what we have here are what you see in the various photos here are these master-slave manipulators, where you basically have an operator outside handling it, and on the inside you have the arm and the end effector, which is essentially a two-point grasp, like tongue-like end effector that are used to perform the operations in there. And on this next slide, you get a sense of really what that looks like. In the larger center picture or photo is a typical end effector, or what the end of what these master-slave manipulators would look like. And the other photos are just to give you a sense of the types of environments and settings that our workers have to work with in working with these hot cells. So to the extent that we can replace these master-slave manipulators with more advanced robotic technologies, we are certainly pursue those. But quite honestly, I think the real opportunity in the near term is our glove boxes, with our eyes set on future applications for the hot cells. We went ahead and decided to combine the two because much of what we would develop, for example, with glove boxes, has a real opportunity to be able to be used in hot cells. The difference is distance and the radiation levels that these devices would see. Just more photos for your viewing on the hot cells. So in terms of some desirable features that we would see for these types of devices, we would like real-time response, so there's minimal latency. What you see is what you get is what we're after. We're looking at very smooth movement where it doesn't, you don't have the jerkiness on like some robotic devices do. We would like to have the sense of touch, so these haptic feedback is certainly a feature that we would like, especially when you start dealing with some of our more fragile components and equipment that we have. Obviously, we want something that's compact, nothing big and bulky that would be very awkward to handle or operate within a glove box. The space within a glove box is at a premium, so we are looking at small, very thin line, slim types of devices. For these glove boxes and hot cells, because we are dealing with radioactive contamination, we are exploring this idea of having them equipped with removable skins, or certainly coverings that can be easily decontaminated or simply cleaned and swapped out. So that alone may end up being part of the challenge, is identifying those types of materials and how to apply them to devices like this. To the extent that we can, we want to be able to swap out these devices. So when it comes time for one to be replaced because of failure, high contamination, whatever the maintenance need would be, that it could be fairly simple to replace them, to remove and replace them with another device. They need to be inherently safe. We don't want anything that can puncture another glove. We don't want anything that can puncture any of our bagged or contained equipment. So certainly from a safety standpoint, while we've removed, hopefully, the worker from that type, we also have to be mindful that other hazards can be presented if we're not smart in the design of our robotic arms. And then in the end, they will be disposed of as a low-level radioactive waste. So to the extent that these robotic arms do not have hazardous components where we have to dispose of them as mixed waste, that is hazardous and radioactive waste, we are certainly desire that as a feature, because the cost for disposing mixed waste is pretty high. So in terms of the requirements, very, very similar to the first integrated research project. The difference here is that as you think about the design of these robotic arms, that you consider what is typical in the industry or what is typical in our laboratories as far as glove box designs, glove port sizes, dimensions. We don't want glove devices that are too highly specialized, where we are not able to use them more broadly within our facilities. And the same thing is true for the hot cells. Moving on to the third integrated research project. Now this is a fairly new concept in this idea about multi-use and multi-user robots, and I'll certainly get into what we want for that. So again, I am the federal point of contact. Tom Nance is the technical contact at the site, and similar to the previous IRP, 2 years at $1.5 million. So what are we looking for here? We are looking for robotic devices that are multi-use and multi-user, MU2, or if you wanted to reduce it to two syllables, you can call it MU2. But nonetheless, we are looking for devices that essentially are dual-purposed in that, one, they are used routinely for facility operations, for environmental operations, but importantly, two, that in the event of operational upsets, emergencies, disasters, any type of accident response, that same device can be deployed to respond to those that different scenario, that off-normal scenario. So in many respects, I put the Superman, Clark Kent Superman type image there, in that, yeah, by day, he's a mild-mannered reporter, but when needed, it can certainly revert to a response mechanism, and that's actually what that's really the fundamental feature that we're looking for at these types of devices. So I mentioned this already. We are looking at MU2 robots that are usable by different professional disciplines. And what I mean by that is I give two examples here. An assistive robot that is used by health physics technician for performing radiological surveys can also be used by a first responder to screen for the presence of airborne radioactivity prior to entering an area or a space. And it's this concept of a physicist to firefighter, where you have a tool that a physicist would use on a normal basis, a health physicist that is, but in the event of an emergency or an accident or some other unplanned event, that it can be, that asset can be reassigned, repurposed, or redesignated to support a firefighter or any first responder in their actions taken to help mitigate that particular risk or that scenario. The other thing is there are some high mobility robots used for routine surveillance and inspection of outdoor or rugged areas. Being able to deploy them readily for search and rescue type operations, or in conditions where, and this is certainly germane to us, where we are entering into unstructured environments where we think we know what a certain area or space looks like or is configured, but we're not sure because we haven't made entry in 2-3 decades. So having this notion of having robotic device that can serve two purposes: one, for normal operations, but two, for off-normal events, is something that we are certainly very interested in developing that technology, but also developing the mindset and the culture where at the time or when an accident occurs or emergency occurs, that we have the tools readily available that people or our workforce is confident in using, and not just confident in using, but also reliable, being able to operate them reliably. So there is this very much this element of dual purposeness behind these types of devices. And for us, we see the benefit in that there is this feature of interoperability, this concept of dissimilar redundancy, and certainly from a response standpoint, defense in depth. And especially when we run into situations where ideally we prefer not to send our first responders in, we would like to be able to deploy robotic devices, at least to do that initial interrogation and initial investigation to help us understand the nature of the space or contaminant that we're dealing with. Very similar to the other IRPs, collaboration with another university, collaboration with another lab or FFRDC. For this one, there is a slight nuance to this. Actually, it's not slight. It's a major difference. In your proposal, what we are looking for to really make this valuable to EM and actually to the broader industrial community, we would like you folks to, or actually not like, we are requiring that you collaborate with one emergency, disaster, or first response organization, such as public safety, police officers, firefighters, paramedics, EMTs, or a special response crisis team like mine rescue, special weapons, basically SWAT, bomb disposal. And then the reason is this: for this truly to be multi-use, multi-purpose, normal versus normal versus off-normal, we really need the insight of these emergency responders and first responders to really make this a viable tool for us. And much like the two previous IRPs, the end product is something that can be readily demonstrated at one of our facilities. Now, again, there are numerous devices, robotic systems, and platforms that exist on the market now. It's just a matter of adapting them and demonstrating their utility to support normal operations as well as off-normal operations. So in many respects, that becomes the challenge and certainly the focus of this IRP. Just some final thoughts. There is a heavy emphasis for us in EM with robotic technology, specifically targeting worker safety and worker protection. So to the extent that our devices allow us to keep injuries and exposures as low as reasonably achievable, we are certainly going to exploit that, and we're looking for your help in identifying those opportunities and making those technologies available to our workforce. In terms of robotics in general, we're at a point now, robotic technologies have advanced to a point that it can be, and we envision them to be, a new tool of the trade, certainly within environmental restoration, environmental remediation, waste handling, special nuclear materials, spent fuel handling, and our D&D. There is no reason why we should not start employing and exploiting those technologies now and integrating them into our workforce. There's my contact information. Feel free to contact me. Again, Tom Nance from Savannah River National Lab is at your disposal also. This is a draft work scope statement that you have in front of you. So if you have questions or feedback, feel free to send those in after this conference or after this webinar, or certainly have the opportunity to ask them now.
Rod, we have several questions that have already come in. The
Okay,
first is related to the IRP-EM2 work scope. Are you looking explicitly or exclusively for humanoid arms or hands, or would you be interested in modular and or multiple effectors?
We are not exclusive to robotic arms and hands. The reason why that was presented in this particular RFP, because that is something that is easily visualized. If you come up with an alternate or a different design, by all means, we are open to that. So I apologize if I didn't mean to narrowly focus this particular IRP on robotic arms and hands, and that's why it's titled telemanipulation. So it can be other types of designs and design features.
What percentage of funds should go to hardware versus software?
That's up to the proposer. So there is, you're going to have to really, the end product again is a functional prototype. So to the extent that you can take advantage of existing robotic devices in terms of hardware, and to the extent that you are able to leverage off of certain software packages to control and drive, then that's something that you folks are going to have to include in your proposal. But we don't have any limit on what that percentage should be or could be.
In your opinion, how many PIs per proposal would you expect to see?
At least one. Actually, so we'll all be, and I'm sorry, I don't mean to be snide in that, but what we are looking for is certainly a university to submit a proposal, but either as co-PIs or collaborating PIs from another university. Certainly that is the bottom line. We do ask, again, that you collaborate with a national lab. They don't necessarily need to be explicitly identified as a principal investigator, either as a co or collaborating, but they certainly can be. There isn't any limit. What we're after is that you folks develop as capable a research team, a technology team that can be assembled to provide the end product, again, which is a functional prototype in all three of these IRPs. So that does include, for example, on IRP 3, where we are requiring that you collaborate with a first responder. They necessarily might not be identified as a PI, but their insight, their perspectives can certainly inform how you shape and how you will ultimately deliver the functional prototype.
For IRP EM3, the collaboration with law enforcement is required. Do we just need to submit a letter of support, or is there some other way that we need to explain that in the proposal?
That's a good question. Quite honestly, I may have to think about that. How do you in the proposal do you communicate the fact that you are collaborating with, and it doesn't necessarily have to be law enforcement. Again, it could be a firefighter, it can be public safety, which are trained in both. Let me think about that, and I will get back to you on, and we will certainly include that in the final FOA or the final work scopes that are issued. But that's a very good question, and I appreciate that. Let me think on that one.
And Rod, we have our procurement staff here who just pointed out that at a minimum, a letter of support from an industry collaborator would be required. So,
okay, but very good.
So that's a minimum requirement at the very least.
Okay. Okay. Well, thank you. So that answers that. And again, so I just want to make sure that on IRP3 in particular, the first responders, they can function or serve merely in an advisory capacity. Again, the idea is to get their insights, get their perspectives on if indeed we are able to develop a multi-purpose robot or robotic device, what are those things that are important to them that you can build into into the functional prototype.
Rod, do you have any advice for making connections with collaborators within the DOE, EM, or National Laboratory Structure, particularly for IRP EM2?
Okay. Yeah. So what I could do, and maybe I'm going to have to consult with you folks, is we can provide contacts, but right now Thomas Nance from Savannah River National Lab, he can certainly provide that type of connection to you and advice to you because he is with our EM's corporate lab, and he does interface on a routine with many of the DOE national laboratories. So if you're looking for somebody that can help advise you and connect you, Tom Nance can certainly do that. Let me think about identifying other points of contacts, i.e. in the other national laboratories. I really would need to consult with them first before I offer up them as contacts. But for the time being, your best bet is either to contact me directly or Tom Nance.
And Rod, to clarify a little bit, any collaborators that we do share with PIs will be posted publicly in order for other participants to also be able to have those same contacts or same connections. So.
Yeah, and the mechanics of that, I really need your advice. I'm not quite sure if I would include that in the final draft work scope or so I do have to explore that. So that's another very, very good question.
Okay, let's move on to the next question. In IRP EM3, do you consider or will you consider humanoid robots?
Yes. So okay, that's kind of a tricky one. So we are looking for robotic platforms. We are not discounting humanoid robots to the extent that, again, they can demonstrate operability both from a normal operation standpoint, or excuse me, functionality from normal operations as well as emergency response. And I hesitate with humanoids just because that's a whole different class, very sophisticated class and complex class of robots that, quite honestly, within the type of work that we have, we can certainly pursue that, and I'm not discouraging you at all from proposing that, but it is one where for us to actually deploy that, there's a lot of other factors that we have to consider. But in terms of fundamental research, technology development, that is certainly not off the table. So I would welcome those types of proposals that capitalize on humanoid robots, particularly those that are within the research community now.
For Scope EM1, do you support the design of new exoskeletons using existing high-power actuators?
So new design, meaning that if you are leveraging existing technologies and components to include actuators, then the answer is yes, because again, we are looking at, while on one hand we would very much like to leverage what has been developed already, that does not preclude us from, or preclude you from taking a look at novel, new types of designs. So, advanced actuators, advanced electronics, advanced semiconductors, advanced materials, for example, those certainly can be features of the technologies in any of these ERPs for that matter.
How many awards do you anticipate awarding in each area?
We anticipate at least one, and a large part of that is, of course, driven by the budget. So what we are expecting for this round is to award at least one IRP in each, or excuse me, one award in each of the 3 IRPs. Each one of those are of particular interest to EM, and so that's obviously why we've included it with this round in the FOA. Is these are areas where we see a lot of opportunity for technology to help influence and improve worker safety and mission execution.
And for some of these questions that we'll answer shortly, the FOA, which is numbered 0001515, which will be coming out hopefully at the end of this week, will clarify how many awards are anticipated in each area, funding amounts, and some of these other rules that we're getting questions on. The last technical question, Rod, and then I have a couple of procedural questions that I need to take care of, is for EM3. Is the radiation mapping and surveying part, or is radiation mapping and surveying part of the scope?
Yeah, it is. Again, what we're looking for is dual use. When I mean dual use, those robotic devices, those integrated systems that can be used for normal operations as well as off-normal operations.
The rest of these questions I will answer since they're procedural. The first is, are we allowed to bid for 2 projects? The answer is, as a lead PI, no. You can bid for 1 IRP project as a lead PI. You can collaborate on multiple IRP projects if you would like. The second question is, what percentage of funds can go to national laboratories? No more than 20% of funds can go to non-university collaborators. That means that in concert, all of your non-university collaborators can have no more than 20%. So if you have 1 national laboratory collaborator, it could be up to 20% of your total budget. Last question, will national laboratories be funded separately or out of the funding limits listed in the draft work scopes? They will be funded out of the funding limits in the draft work scopes. And as I stated before, that can be a maximum of 20% of your total budget.